Hello everyone. Welcome to my floor, I guess. But today we're going to actually be talking about Aeroshells. So what am I talking about when I talk about an Aeroshell? Well, I'm talking about basically the outside of a capsule or a spacecraft or probe that enters an atmosphere. One of a very notable example, oh boy, this is a little out of focus, is the Mars Science Lab, which is out of focus still, so give me a second here. Whoa. Okay, good enough. And this was the Aeroshell design used for the Curiosity and Perseverance probes. Obviously, we're going to be looking at scaled down versions because I've printed out a bunch. But this is basically what I imagine when I think of like a Mars lander. And a lot of similar probes that went to Mars had a similar general design. Well, we can actually look at the real design. This is a paper from the American Institute of Aeronautics and Astronautics, or AIAA. And this is aerothermic dynamic design of the Mars Science Laboratory backshell. So, what's notable is we have this 70-degree aeroshell. This is the entry side of the EDL. That's the really hot part. That's the part that experiences the most dynamic force and pressure and things like that. Basically, all Mars landers use that same design. There's some variance, but mostly for successful probes anyway, it's always the 70-degree. So for MAGPIE, I pretty much copy that. Now after that, they have basically 3 sections. It's a little hard to see here. And, here's the model. And I think actually on the model you can see the 3 sections on top. So you've got this cone here, you've got a smaller diameter cone here, and the cap. Now what's used on the Mars Science Lab is you've got basically this one section that houses the ends of the rover and the beginning of the sky crane, and the same goes with the second, although that's going to be more for course adjustments because this has your thrusters. Now in here is what they call a radiodome, and that's because it's a completely different material. And so it's just made just so radio can pass through it, because the typical ceramic like TPS type insulation is not effective for transmitting radio waves. So their solution, which I actually really like, allows for you to put antenna right in here. And with this type of design, you can have several different types. You can have helical antennas, which are very cool, and would quite literally work very well for this. You can have a patch antenna on top, which are directional or monodirectional, depending on the design and everything. So that would allow for, you can also put a J-pole or something in there, a dipole even. So there's a lot of different designs that I really like about this. Okay, well for the MAGPIE project, remember this is the size of a car, if not larger, because a rover is about the same size as a small car. However, I plan on having 6 MAGPIE probes. And they kind of look like this, with deployed solar panels. We'll look at that later. So, I believe this is a diameter of 4.5 meters. So this is quite small. This is, I don't want to guess the actual scale of this. I feel like that would be a bad ending. So, the original design of these probes were that they were 320 millimeters across. They're a bit larger than that now, but that's okay. And so what that means is the way and the profile of these, it's actually optimal, where we have the antennas fold up into here. And then this kind of creates that wedge shape of the aeroshell. And so the probe itself is actually stored upside down, which I'll show in a CAD later, in a later video. But it's actually stored like this. And then when it's deployed, it flips around. So with that, means we have a diameter at maximum about 800 millimeters, which is, just, 0.8 of a meter, which is, just out of frame, about that big. These are small probes. These are not large. And so our first iteration with the Aeroshell design for testing was Gen 1. It's pretty simple. We've got our roughly 70-degree cone here, and a badly printed very small lip. And then we have a rather steep angle, as you can see, compared to March Science Lab. This is a bit steeper and taller. And we have just a flat section here. That was mostly to allow for a large surface area for antenna, but I realized I actually needed more space than this, because the probe itself is also going to use up some of this space. Well, and then I have to have parachutes, and well, how am I going to deploy the parachutes if I have just a single shell? That adds complexity. Or rather, a higher likelihood of something going wrong. This is actually low complexity. The other problem of this design that I didn't really like, it has a rather sharp nose here. So, how do we address that? Well, we develop Gen 2. Gen 2, well, it's a lot more pancake. It's got a more dull nose. You might be able to see that the diameter of the flatness is larger here. It's about double. And we actually have two stages. We have two cones. We have this large cone, which is far steeper inwards, and this rather lazy one. And then we have a smaller cone here. I genuinely really like this design. It allows for us to put antennas in the second if we want, or this top section. And it's very stable in my CFD simulations. However, it's kind of awkward. Like, it doesn't have that much space, and for letting it go, because this is roughly how they'll be stored, is always in this orientation, and when deployed, they'll have arms that go out. And this is because we're going to have thrusters here. They're going to be mounted facing that way. And so just to make sure that they can get away from the probe, because let's say, two arms open, you might still be able to get out. So with this, it's kind of just an awkward shape, because sure, it's large and wide, but there's not actually that much space to do that. There's more usable space in this more simple design. So, well, we come up with Gen 3. Gen 3, we're definitely starting to get there we're a lot closer to the Mars Science Lab here, because now we have this added section on top. It's very small in comparison to the same size, but this one has a larger diameter. This is about 800 millimeters across, and this is exactly 1 meter. Why? I wanted more space, and the main orbiter can size it, and the fairing can size it, so we went with the maximum of what I was comfortable designing with. Now, this is still a pretty strong lip. There's not much rounding. You might be able to see there's rounding here. And we don't get quite enough space to actually really do. We still kind of suffer with the same weird shape. So that's when we come up with Gen 4, which is pretty much our final design. And as you can see, again, very similar. We have an increased size on all of these cones here, meaning that the diameter, or the radius has been, the angle, sorry, has been opened up a little bit more. And let me just walk through kind of like the stages of these aeroshells. So we'll enter the atmosphere, and then after we've reached about Mach 3, we will deploy the drogue chute, which comes off of this caps here, and we'll have our antennas along here and here. And then after the drogue chute is deployed, we can slow down sufficiently to deploy the main chute. So the drogue chute pulls this entire section off, and then it deploys the main chute while it's doing that. It's a kind of smaller chute to create enough drag to pull this. This shell in itself makes its own chute, effectively. And we are still secured with the bottom heat shield here. Because, well, this is a really good, cone here, blunt cone, to effectively slow down the probe. And so getting rid of it would mean that it'll just fly back up, because it's going to have minimal mass, but a really big CD in area. So we first get rid of this section, and then we deploy the main chute. We slow down enough where we can deploy the bottom. And because this is our final design, let's create a similar-ish scale. This is a 1/20th size. Again, this is 1/10. This is 1/10 actual scale. So these probes are tiny. So this is 1/20th. This is 5%. And at that scale, here's the probe. Again, super small. This is 5%. And that's what it'll look like landed. Just like that, if you can see. But yeah, so that's kind of the evolution of our aeroshells. Sorry I don't talk about too much about how specifically it may have been designed, but it's just kind of how it goes. I'll talk about more in a later video about the EDL, because I'm really excited to share that simulator. It's just over 2,000 lines, I believe. So I'm very proud of it. Thank you very much for watching. Have a great day. Bye bye.